Okay, welcome to some new slides. These are on graphs and graph theory. We're going to draw a lot of pretty pictures for these slides. Okay, so the first thing that I want to do is just overview graph theory. I can explain to you that this thing that I saw on Instagram a year ago is a pyramid scheme because of graph theory. So this is exciting. Did you see this maybe? A bunch of my friends posted on their stories this text, and they wanted to participate in a book exchange program. So all you have to do is buy your favorite book and send it to a stranger, and then somehow you're going to receive about 36 books back to you. Crazy. And there'll be other people's favorite books. Please message me, get in on this, and just everybody buys other people's books. Doesn't this sound great? Well, this is a pyramid scheme, and it will fail eventually because of this reason. All right? So we can model these book exchanges with a directed graph. So a graph with arrows, nodes and arrows, okay? Kind of like how we were drawing relations. So here is the poster. The poster is a node in this graph. The person who's asking you to send other people books. And here's you, who's looking at their message. Like, hey, I want to participate. And so the person who the poster responded to is the person that you will be sending a book to. That's kind of how that works, and so there's an arrow in that direction. And then the people who respond to you, boop, 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 saying, I want to participate, they are going to send books to the poster, the person who you got this message from. And so this is how people are getting books, okay? Getting books sent to them. And you can imagine that there's a long chain going on here, a bunch of people sending other people books. And it's just going in that direction, and all of these arrows pointing that way, okay? The issue is, the reason this is a pyramid scheme is because there's going to be a last person, okay? There's going to be some people at the edge of this graph who, everybody who they send this to, like they copy and paste this text and send it out to their Instagram followers, there's going to be nobody who has not already participated. And so there's not going to be any arrows coming in this way anymore. And so that last person is going to be sending books to people somewhere, or just one, I guess. That person's just going to send a book in and never receive any in return. So sad. So that is a pyramid scheme, and we proved it with graph theory. So lots of dots and arrows. That is going to be the topic of this set of slides today. Okay, so let us begin. So we talked a bit about directed graphs in the relations slides. It's just dots with pointy arrows. You can have dots without arrows as well. Those are called undirected graphs, okay? So let's talk about those. The only difference is that the edges, right, it's always vertices and edges, they don't have to like have a direction. We get rid of this arrow, and it's kind of like bidirectional. You can think of it that way. You could go either way along this edge from A to B. You can go that way and go that way. It's like you can move around. It's like a street, okay? So a graph, an undirected graph, consists of a pair of sets where you have V and E, just like for directed graphs. So you have vertices and you have edges between the vertices, okay? V is a set and E is a set. Let's list the E and V for this graph over here, okay? Let's talk about that. So what are all the vertices of this graph? It's all the little points that you can move to. So it's A, B, C, D, and E. And what are all the edges, the ways between points, the lines between points? What are those? Those are, well, you have an edge from A to B. There is no direction, so it doesn't have to be a pair like this, like it was for directed graphs. It can just be a set of two things, like, okay, it's A and B. It's a set of sets. There is an edge between A and B and between B and A. It's just one big thing, okay? Sets are unordered. And then we can also model this one in our set of edges, B and C. Doesn't have to be in any proper order. And that is our set of edges. Just follow all of that, like BE, ED. Talk about them together. It's an edge connects two vertices. So it's a set of subsets, which each contain two vertices. Those are our edges. That's how we can represent them. And sometimes you have things called weighted graphs. That's where, like, you know how long the street is. There is a weight or a cost to move between vertices. Okay, so let's make up some weights here. Like let's say that from A to B it takes 5. It's 5 weight to go there. It's like 5 miles from A to B, for example. Maybe from B to E it's 12 miles. It's 42 from A to C. You can do all this. 8, maybe a 5 again. And you can totally have 0 weights, negative weights, not a big deal. Like from B to C, maybe, I don't know, it's downhill or something, and so both ways. And it's negative 17 cost. It's very easy to get from B to C. Like people pay you to go there. That's how that works. You can have negative edges. That's not a problem. Okay, so that's a weighted graph, where you put some weights or costs along the edges. All right. Let's get into fancier looking graphs. This is like a normal looking graph in my mind. This is a weird looking graph, especially when it's undirected. And let's talk about why. Hopefully you can kind of tell. You have things called parallel edges, possibly, in a undirected graph, which is kind of weird. It's like 2 ways to get to the same place. That's a bit odd. So you can have multiple edges between the same pair of vertices, okay? That is weird. And so maybe like one is like the normal road and one's like a toll road that you have to pay for, but the distance is shorter. So like you got to pay $5 to go on a straight path maybe. That is a parallel edge. That seems weird, but it's possible to have it. You can also have self loops, just like reflexivity in directed graphs / relations. You can have an edge between a vertex and itself, and it looks weird because there's no arrow. But that's possible. There's a way to go between you and yourself. That's totally fine. And then a simple graph is any graph that does not have those things. So a graph that does not have a parallel edge or any self loops. So this is a simple graph, and this is a non-simple graph. Maybe it's a complex graph. Who knows? So that's some more terminology. These graphs you won't see very much in the wild, though. Okay. So for regular looking graphs, let's have some more bold terms. Just there's a lot of terminology up front. This is a math class. You know that by now, right? So let's talk about all these new terms. So if we have a way of getting between 2 vertices, if there's an edge, we also say that they are adjacent. Okay, and that's the adjective that we choose. So like A and B here, they are adjacent. There's a way to get straight from there to there. A and B are adjacent, we say. Let's see here. And so are like B and E. B and E are also adjacent. That's not a problem. Okay, you can get straight there. B and E are adjacent, or I'll just say, quote, quote. You can have neighbors. A vertex C is a neighbor of vertex B if and only if BC is an edge. So all the neighbors of, I don't know, all the neighbors of B are A, E, and C, right? Those are all the things you can get to by an edge. That's what it means to be a neighbor. You live right next to it. There's a path to get there. There's a single edge to get there. Yeah, so that's what neighbor means. I should also say that like A and D, for example, here are not adjacent. There's not an edge there. Are not adjacent. Okay, so that's adjacency, neighbors. We can talk about the degree of a vertex in terms of the number of neighbors. So for example, B, because B has 3 neighbors, we say it's of degree 3, okay? Its degree is 3 because B has 3 neighbors, okay? That's what we can say. You can also talk about the degree of the graph. The total degree of the graph is the sum of the degrees of all its vertices. So it kind of talks about this. This is one number that talks about how connected everybody is to one another, how nice the neighbors are to each other. So the degree of this graph, of the whole graph at once, is, let's see, so we got A has 2 neighbors. Oops. A has 2 neighbors, so that's 2 plus the 3 that B has, plus C has 3 neighbors, plus D has 2 neighbors, plus E has 2 neighbors, okay? So 2, 4, 6, 7, 8, 9, 10, 11, 12. The degree of the whole graph is 12, it seems, okay? So that is that. if you have a graph, you can make a smaller graph out of an existing graph. That's called a subgraph. So you make a graph with vertices and edges that are both subsets of the original graph G. So H is a subgraph of G if the smaller vertices are a subset of the original vertices and the smaller edges are a subset of the original edges. And it's subset or equal to, so a graph is also a subgraph of itself. It's like a less than or equal to relation. So a subgraph just means you take the same graph and you throw some vertices or edges away. Potentially none. Okay, so for example, like let's pick out AB, AC, and CD, and let's skip E. So we'll throw away E and all the other edges that we don't care about, like this one and this one. So this is a subgraph where we have all those edges that we care, or all the vertices that we care about to link together still, and boop. None of the ones we don't want. So A exists, B exists, C, and D. This is a subgraph of the original graph. Okay? You just throw some stuff away. That's not too bad, I hope. So yeah, you could model a lot of things with graphs, like ways to get to places, interconnectedness. So here's a fun little graph of countries. And we're of course not done with terminology because that would be too easy, of course. So let's talk about a little bit more terminology, and then I can finally ask you some questions to make sure that you're getting it all. So let's talk about really cool looking graphs. We have names for these things, okay? So you can have a regular graph. Now that we know about all the terms that define these, we're ready. So if you have a regular graph, that means that every vertex has the same degree. This vertex has degree 3. This vertex also has degree 3. This vertex has degree 3. It has 3 neighbors, right? All of them have 3 neighbors. So this is called a 3 regular graph. That's not too bad, I hope. So that's cool looking. And then there are other graphs like this one, KN. That's called the complete graph, I guess K for complete. Complete graph on n vertices. So what that means is that is, if this is K6, right, that means you have 6 vertices and every possible edge that could be there is there. Like every vertex is linked to every other vertex. They're all neighbors. They all have edges to one another. And so this is K6. That means everybody has degree 5. Right? They have a way of getting to, every node has a way of getting immediately to every other node. And this is also sometimes called a clique. I don't know why it's pronounced clique. Maybe that's because it's comes from French people, but usually in English we pronounce that word as click, right? But we say clique in graph theory. And this is also sometimes called a clique of size 6, for example. Has every possible edge that could be there. So that's KN, and this last one is the weirdest one, KNM. So let's talk about it. So there are 2 numbers separated by commas, and it's kind of like a complete graph, so that's why it takes a K as well. But it kind of separates those 2 things. So here is K34, for example. I hope you see that. So on the left side, you have the 3 nodes, and then on the right side you have 4 nodes, 4 vertices. And then you kind of like draw a line, and then everybody on the left is connected via an edge to everybody on the right, and vice versa, right? So there's a way for this node up here to get to every node on the right, and same from the right's perspective. There's a way for this node to get to everybody on the left, but there is no way, there is no edge between people on the left side. Okay, that doesn't exist. So it's kind of like you're sectioning things off. So the vertices, they're divided into 2 sets, one with m vertices on one side and n vertices on the other. There's no edges between vertices in the same set on the same side, but there is an edge between every vertex in one set and every vertex in the other. Okay, so that is K34. I hope that makes enough sense. So I'm finally ready to give you some examples for you to try. So here's a question for you. How many edges are in K34, and is it a regular graph? Okay, remember the definition of regular. Maybe pause it for a second here to look at it. So take a look at that and tell me. Alright, so K34 means 2 sets. 3 on one side, 4 on the other. there's a way to get there. This has 3 edges. This has 3 edges. Oh, sorry, 4. What am I doing? 3, 4. Forgetting about the bottom dot for some reason. 1, 2, 3, 4. 1, 2, 3, 4. So how many are there? So 4, 8, 12, right? There are 12 edges. 3 times 4. That's easy. There's 3 times 4 equals 12 edges. That's an easy thing to compute with this kind of graph. And then also, is it regular? So that means, does every vertex have the same degree? These all have degree 4. That seems promising. But sadly these, because I got to go to everybody on this side, and it's a smaller side, those only have degree 3. So everybody over here has degree 4, everybody over here has degree 3. They don't match, so it's not regular. Okay? So sad. But that's just following the definitions. Hopefully that wasn't too bad. Okay? So that is fancier graphs. And now let's talk about expressing graphs. This was K34, by the way. Let's talk about expressing graphs inside of a computer, because that is something we very much care about. Okay, so they make for nice data structures. There are 2 ways, actually, 2 main ways of storing a graph inside of your computer programs. So there are 2 main ways. It's called adjacency list representation and adjacency matrix representation. So here is the same graph that we want to represent. Okay, and I'll show you both ways. So the first way is called adjacency list. It tells you how many, or it tells you what people are next to what people in a very compact way. It only stores the edges that exist. Okay, so adjacency list representation, you have a list of vertices, right? You have a map, really. Each vertex knows all of its neighbors. It holds a list of its neighbors. So it would look like this. This would be the type. It's a map from, say, strings, the name of this vertex. So A, take A to a list of other strings, the B and C that it's connected to. Does that make sense? And so you could define this in a single type. You could define, instead of saying map string list string all over the place, you can just say typedef to give an alias for that fancy type and call it adjacency graph. And so then, from then on, you could use that typedef and just say edge graph G, and then just fill it up. That's what a typedef does. It gives you another way of writing a long type. You can shorten it to that. So that is how you could declare it now. And then you always want to map your names of vertices to all the things that are connected to it. So A maps to the list B and C. B will map to the list containing A, C, and E in some order. Okay, A, C, and E, that's fine. And so yeah, you need to use either a map here or an unordered map in C++. You need some kind of key value pair going on there. Okay, so that's an adjacency list representation. I hope that makes sense. Like the vertex D would map to its neighbors C and E. It's just a list of those. So you're only storing the edges that exist, okay, for each vertex. And then finally, you have a matrix representation as well. That's another option. Okay, that is a grid. It's an n by n grid. We can't really give names to the grid, so instead of A, we have to say 1. Instead of B, we have to say 2. So it's like numbers. We've lost the names of these vertices, but maybe they're not too important. But the matrix representation is always n by n for your n vertices, and it's a matrix whose values at each entry is either 0 or 1, true or false, right? Saying whether or not there is an edge there. So, for example, this edge between 1 and 2, 1, 2, boop, we got to put a 1 there. And then same 2 and 1, you also got to put that same 1 there to say it. It's a, oops. This reflects across that axis, right? You have to put 2 entries for every edge, just like you had to put 2 entries for every edge here as well. Hopefully that makes sense. So yeah, that is adjacency list and adjacency matrix representations. You kind of have to use a bit more space to store the matrix, right? Because you also have to say what's not there, zeros in addition to what is there. where adjacency lists only store what is there, okay? And so this kind of wastes space. You can make it as like a 2D vector of booleans, okay? And so this kind of wastes space if there's not a lot of edges, right? And the fancy word for graphs with not lots of edges, not a lot of edges, is called a sparse graph. It's barren. It's sparse, okay? And that just means not many edges. Boop. And so we tend to prefer adjacency list representations for that reason, because most graphs don't have a ton of edges. Okay, so with that in mind, take a second to look at this graph. Here it is, and define it. How would you represent it as an adjacency list, and how would you represent it as a matrix? So draw those out, please, and then we'll talk about it. Okay, so let's do adjacency list first, because that one's not too bad. It's always a map between keys, which are the names of these edges, so A, B, C, D, and E. 1, D, C, D, and E. And then it maps to a list of all the things that are connected. So A is connected to B and C. Those are the edges. So the list holds B and C. Okay, and then B maps to, it has edges going to A and C, so we're going to store it right there, A and C. C goes to, B, A, E, and D. Good for you, C. B, A, E, and D. You can put this in any order you want. D goes to C and E, so it would map to that list, and then E finally goes to C and D. Okay, so that would be an adjacency list representation of all the edges that exist in this graph. The matrix representation, remember, it's got to be n by n, where n is the number of vertices, and let's, instead of using numbers, let's just be fancy and use the names, because why not? Just like A, B, C, D, E, A, B, C, D, and E. Technically, these should be numbers, though. So is there an edge between A and itself? No, there's no self loops anywhere. But is there an edge between A and B? Yes, there is. So we got to put a 1 there. And a 1 in the opposite way, because there's an edge between B and A as well, right? It's the same edge. So it always reflects like that. So there's a bunch of zeros here. Let me try and line these up. Bunch of zeros here. And then we got to add 2 1s for every edge here. So B and C as well. So there's an edge between B and C. Same with C and B, just like that. A and C. Edge between A and C, E and C, E and C, and C and E. Gotta put a 1. And then E and D, and then D and E as well. And then C and D. So C and D and C. So I think if I did it correctly, that counted for everybody. And so then there's just a bunch of zeros representing the idea that there are no edges between those other things, those other pairs of vertices. Okay, so those are the representations. That's how you might store a graph in your program. Okay, so that's that. Now let's keep on trucking. I have even more terminology now because we haven't talked about how to move around a graph. We've talked about edges, like a single way to get from one place to another place in one step. But you can follow edges, can't you? So let's talk about that kind of terminology. You can follow multiple edges at once. So here are a bunch of new bold terms. I'm very sorry. So a walk, we say, from some starting vertex to some ending vertex in an undirected graph is a sequence saying which vertices we went to and which edges we followed to get to that vertex, because there might be multiple options, right? Because you might have like parallel edges. You got to say which edge, please tell me, did I take to get from here to here. Okay, so that's a walk. You got to say what's going on. Okay, in an undirected graph G, it's a sequence of alternating vertices and edges that starts and ends with a vertex. So starting at vertex 0, I move to vertex 1 via this edge, and then I move to vertex V2 from V1 via this edge, and so on and so forth until my final ending vertex, vk, I got there from this edge, from vk minus 1. Okay, so that's a walk. It's just giving all the information that you need to say exactly what happened. Okay, in a simple graph, you don't have to say what edges you followed, right? You can skip the edges, can't you? Because there's only one way to get from A to B. There's only one edge from A to B right now. I hope that makes sense. So that's a walk, and we, a lot of the time, care about the length of a walk, okay? And so, in a non-simple graph, you have to specify those edges, and if you go somewhere, you care about how many edges it took you to get there, right? So maybe to go from A to C and C to E, like that's my way of going from A to E in total. That was a walk, and it was of length 2. Okay, that's the idea there. What else? What else? You can have a closed walk. A closed walk is where you kind of went around in a circle. It's a walk where the first and last vertices are the same. So, for example, here's a walk from a closed walk from A to B to C back to A. That's a closed walk, okay? Because I ended in the same spot. Every other walk that doesn't end at A, it's starting at A, is called just an open walk, okay? It's where their ending vertices and the starting vertices are different. All right. A circuit is a closed walk in which no edge occurs more than once. So here is a closed walk that kind of is not a circuit. Like I can wrap back around, take 2 laps back to A. That's a closed walk still. A circuit must only be like this, right? You can't go along the same edge multiple times. That's kind of wasted work, right? And so a circuit makes it so that you don't waste work like that. You only go along one single edge at a time. You don't duplicate using edges, okay? So that's a circuit. And then finally, this is the word that we use a whole lot in graph theory. It's called a path, okay? It's a walk where no vertex or edge occurs more than once. Because why would you want to go back to the same place along maybe a different route, right? So here is a circuit that's not a path, let's say, or like a walk that's not a path. Let me give an example of that. So here is, I don't know, we might have to have multiple edges. Let's do that. So that's an edge, and then that kind of thing. That's a path. Or, sorry, that's a walk, but it's not a path because I went to B a bunch of times, okay? That's a walk, but not a path, because I duplicated going to that vertex a bunch of times, okay? But I didn't follow any multiple edges. So a path is kind of like the best thing. It's a walk where no vertex or edge is traversed more than once. So here is like one of the longest paths that you can have in this graph, because the second you add another edge, you go back to a vertex that you've seen before. So that wouldn't be a path, right? Oops. There we go. So that's a path. And then finally, cycle is also a very important term. A cycle is a circuit. So I'll go back to this. A circuit of length at least 1 in which no vertex, except for the first and last, because you have to duplicate those, of course, occurs more than once. So the first and last vertices are the same. So it's like a path that ends at the same spot. Okay? A cycle is a circuit of at least length 1 in which no vertex occurs more than once. So this would be a cycle. Okay? It's a way of going back. This, for example, going back and forth like that, would be not a cycle, right? Because you kept on visiting the same vertex a bunch of times. So it's kind of like the most efficient way to make a loop. That's what a cycle means. Okay? So that's a lot of terminology. I'm very sorry about it. I have one last slide on terminology before a question about it. Okay? And these are kind of like intuitive terms, so I'm happy we can at least get to here. So we say, we can talk about, now that we know about paths and ways to move around graphs, we can talk about is there a way at all to get from one place to another place? And that idea is called connectedness. So we say that two vertices are connected if there's a path between them. There's a way to go from I to D, so there's I and D are connected. Okay? For example, everybody here can get to everybody else. So this is like the whole graph. but all these guys can get to each other. So this whole set, like A, I, pick out any two, H, D, and F, those are all connected, right? That whole set is connected. We can say that, yeah, we can even use that kind of terminology. A set of vertices, we say, is connected if every pair of vertices in it is connected. So everybody here, pick out any two, they're all connected. A to D is connected, F to I is connected, they're all connected to one another, okay? And then we can say that a graph itself is connected if everybody, all of its vertices are connected, and it's disconnected otherwise. Unfortunately, this graph here, let's call it G, this graph is disconnected. Because there's ways to get around for all these people. They're all connected. These are all connected. I guess B is connected to itself, but there's no way to get from like B to F or something. That's unfortunate. So that's a disconnected graph. And if you have disconnected graphs, it's often a good idea to ask about, okay, what are all the other sets? What are all the sets of connected things? Like, it kind of partitions the graph, right? Remember that word? Kind of partitioning the graph there. So we can talk about things called connected components, okay? That is a maximal set of vertices that is connected. So for example, this whole thing is a connected component. This is a connected component. Oops. This is a connected component as well. All these vertices are not a connected component because it's not maximal. You could also add in F. That is also connected to everybody else in that set. Okay? So those are connected components. That's the idea there. Okay? So sorry about all the terminology. It's just a new topic, and so a lot of people have been doing work in this area. They've made up a lot of words. Finally, I have a question for you, though. So take a look at this undirected graph. Please tell me, what is the maximum length of a path in it, first of all? And tell me, maybe give an example of a path of that length. What's the longest path that you can make in this graph? What's the maximum length of a cycle you can make in this graph, where you can wrap around, right? Give an example. And then give an example of a closed walk of length 4 that is not a circuit, right, to differentiate those ideas. And then give an example of a circuit of length 0 in the graph. That's possible, right? Circuit is a closed walk in which no edge occurs more than once. Well, a circuit can totally have length 0, right? Go along 0 edges. That's possible. So give this a try. All right, maximum length of a path in the graph. Let's talk about A. Well, a path cannot duplicate vertices or edges. So at best, how many vertices do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So at best, we can have a path of length, right? Length 8, right? Going between each vertex. And so we could do something like this. Boop, 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 boop. Can't have a longer path. That's the longest one. So that's A. B. What is the maximum length of a cycle in the graph? So a cycle can not duplicate vertices again, but it except for the starting and ending one. So I can kind of take what I did. The maximum cycle that we could have is one that visits everybody and wraps around, right? Let's see what we can do there. No vertex occurs more than once except for the first and last ones. So we can't actually have a cycle visiting everybody, can we? Because this guy is sticking out right here, the C vertex. There's no way to get a cycle that only duplicates C at the end, because you got to go through I again. You see that? So C is kind of left out. The best cycle that we can have is one that skips C. Okay? Starts at anybody else, though. So that's one way to do it. Oops. That's B. Give an example of a closed walk of length 4 that is not a circuit. So a circuit is when you don't duplicate edges. A closed walk just means you start and end in the same place, potentially duplicating edges. So that's the hint, right? So here is a closed walk of length 4. I don't know. Let's go around and be like A, B, B, E, back to B, back to A. That is a closed walk. Whee. But it duplicates edges. So sad. So it's not a circuit. Okay? And then finally, a circuit of length 0 is totally possible. Just start at one place and stay there. Right? Don't move. So that is valid according to the definition for D. A circuit can have length 0. You started at vertex D, for example, and you stayed there. You didn't go anywhere at all. You're still there. So technically a circuit. All right? So that is some good examples, I hope. And I hope all these terms are starting to sink in now that we're getting practice with them. Okay, let's keep on trucking. I have 2 more main slides of information for the day, and then I will stop overloading you with terms. All right? So the next thing to talk about are special kinds of cycles and paths. Hamiltonian cycles are the first ones, and then we'll talk about Euler circuits as well. So a Hamiltonian cycle in a graph is a cycle that includes every vertex in the graph. That's a nice kind of cycle to have, right? So can we find a Hamiltonian cycle in this graph, for example? Let's see. It is a cycle that includes every vertex in the graph. So for example, I don't know, you've got to include that one, that one, that one, that one, that one, and that one. That is a Hamiltonian cycle, it would seem. So that's a Hamiltonian cycle. And then a Hamiltonian path is a path that includes every vertex. And so a very easy way to get at a Hamiltonian path is start with a cycle, if there's a way to get one of those, and just remove the last vertex so that it doesn't wrap around and make a cycle, right? Boop, 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 boop. So that is technically a Hamiltonian path. So those are like the best kinds of paths and cycles, ones that visit everybody, every possible node once. Okay? So now we have terms for like this one. That was a Hamiltonian path, wasn't it? It's a path that includes every vertex. Cool. And then the last term that I want to teach you is Euler circuit. These are all about undirected graphs, by the way. An Euler circuit is a circuit that contains every vertex and every edge. Okay? And so the reason I picked this picture and I drew this specific graph is because in either first or second grade, I don't know if they do this anymore, but they put little brain teasers on the back of the little school milk boxes, and it was asking, essentially in first grade terms, could you find an Euler circuit for this picture, for this graph, which is kind of cute. And so this is all coming full circle in my life now. So let's see if we can find a Euler circuit, I might have forgotten how, for this graph. We got to draw it. We got to visit every vertex and every edge just once. Okay? That is the idea. So I think it's something like this needs to happen. Boop, boop. And I did it upside down, but I think you can imagine that you can do it the right side up. Let me see if I can quickly do it that way. Oh gosh. Is it like this? Boop, boop. No, I did it upside down again. Sorry. But I think you can get the idea. That's how it should have been. Just reverse it. Okay? That is how you can do and find an Euler circuit in this graph. It's a circuit that contains every vertex and every edge. But you can't duplicate it, so it's got to be just once. So that's kind of cute. Okay? All right. See if you can find a Hamiltonian cycle now in this graph. That's a cycle that visits every vertex. Okay? Do you see it? How can you do it? I'm sure there's plenty of ways, but if you want to visit everybody, boop, 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 you just try things. Boop, boop, boop. That works. That is a Hamiltonian cycle. And oops, I have to finish it off, don't I? Not a path. That was a path. Here's a cycle. Yay. Okay. So that looks like a good Hamiltonian cycle to me. All right. I don't know if there's others. This is symmetric, so maybe like if you start on the bottom and do something like this, that also would work. But that is the idea. So that's one way to do. Okay, there are potentially multiple ways. And then finally, another idea of moving around a graph in a special way is called traveling salesperson. You might also hear this called, it used to be called traveling salesman. We don't like saying that these days, right? Because anybody could be a salesperson. So we call it traveling salesperson instead. And this is the idea. So if you have a graph and it's weighted, so you have weights on the edges, numbers, that's like the cost of traveling from one place to another. You can ask, hey, what is the shortest possible route that visits each city exactly once? Because like it's a graph that it represents a map, okay? That visits each city exactly once and returns to the origin. So it's essentially finding a Hamiltonian cycle in your graph that is a map, but also with the weights involved. Like we want the minimum possible weight. Like we want to spend the smallest amount of money on gas. Okay? Does that make sense? So it's how can you visit every vertex in a way that minimizes the total weight along all the edges that you follow. Okay? That's the idea. So this is actually a very hard problem to solve. Okay? This is like a traveling salesperson solution for visiting all the state capitals. This is the most efficient route if you could travel in straight lines. So that's involving distance, where the weight is distance. But yeah, you can totally model this with a weighted graph. You can try all the different possibilities, right? All the different permutations of edges that you could follow. Like I could do this one first, then this one, then this one, then this one. There are a bunch of different ways that we could start and visit everybody. But there are n factorial permutations, and that is essentially exponential time. That's horrible, okay? So that's quite sad. And it just so turns out that to solve a traveling salesperson problem on an arbitrary graph with arbitrary weights is insanely hard. You can't really do better than factorial time, okay? Our best algorithms for solving this problem, for finding the smallest weighted route between a bunch of nodes in a graph, all of them, and coming back to the start, those are all exponential time. Oh man, that's crazy. That's a very hard problem. We haven't proved that it's any easier. If you've heard about this, if p is equal to np, then maybe there's an easier way, there's a secret to solving this traveling salesperson problem in a very quick way, but nobody has found it yet. And so all signs are pointing to it being a very hard problem for all eternity. So that's kind of cool. So that's a very difficult problem that we can now express with our knowledge of graphs and graph theory. So with that, a lot of new terms, I'm very sorry, but that is where I want to stop for the day. So we are now experts on graphs. We'll come back and talk about more algorithms to actually do stuff with graphs stored inside of our computers.